Welcome to Circuits Decoded. I am glad you stopped by. My name is Debajit Basak and I am an analog circuit designer with a PhD and about 8 years of experience in analog and mixed signal design. Through this channel, I am excited to share some of the coolest techniques I have learned over the years, along with a few stories of my own journey in the fascinating world of circuit design. So whether you are starting out in IC design or gearing up for an interview, I hope you'll find something here that sparks your interest or helps you level up. Now, right off the bat, I want to acknowledge that there are a few good YouTube channels discussing fundamental theories of circuit design. However, in this channel, we'll go beyond that. In particular, we'll be covering both basic and more advanced topics such as ADCs and transceivers. The focus will be less on equations and more on building concepts and intuitions. We'll provide design examples and sometimes simulations to check our understanding. We'll also link concepts to published research works in top-tier journals and conferences. I'll also discuss some common types of questions asked in the interviews. There will be no particular order to the videos. However, I'll try to structure them in series like noise, stability, etc. And finally, I'll provide references and links. So if you want to dig deeper into the topics, you can just look into them. With that said, let us begin our first video in the Analog Techniques series. The topic for today is bandwidth extension techniques in analog design. This will be a two-part video discussing mainly two of the most widely used techniques in high-speed circuit design. So we are all familiar with the active negative feedback technique to increase the circuit bandwidth. There is usually an amplifier and some sort of feedback network, which is usually passive, around it. The feedback essentially increases the bandwidth by a factor of 1 plus the DC loop gain, while decreasing the system gain by the same factor, as you can see in this expression below. However, the amplifier usually has more than one poles, a dominant pole and a few non-dominant poles. The non-dominant poles are the ones which make it difficult to stabilize the amplifier at high speeds, which ultimately limits the gain bandwidth product or the unity gain frequency of the system. The two techniques that we'll be talking about in this video and in the next part are about passive techniques and method of cascading. These are open loop techniques and therefore do not suffer from the same gain bandwidth product limitations of the closed loop amplifiers. And they are widely used in applications that require tens of gigahertz of bandwidth, such as wireline transceivers. Okay, before diving into that, let's refresh our understanding of a second order low pass system. This is a transfer function of a two-pole system with no zeros and a DC gain of k. The poles omega p1 and omega p2 can be real or complex conjugate pairs. After some simple math, we can get a more familiar expression of the denominator as shown in equation 2. The denominator is a quadratic function where zeta is the damping factor, q is the quantity factor, omega n is known as the natural frequency, and zeta and q are related by the expression shown below. Now, there are some textbooks that use the expression with zeta and others use the one with q. So it is useful to know this relationship. Now, by comparing equation 1 and 2, we can get an expression for omega n, which is equal to the geometric mean of the two poles. Next, if we solve the quadratic equation, we can get a solution for the poles as well in terms of omega n and zeta. Now, from stability theory, we know that the poles of the system dictate the stability of the system, which in turn depends on the factor zeta. So designers often make use of zeta to control the stability of the system. To get a better understanding, we need to look at the time domain response of the system. So if we look at the solution of the two poles, we can think of a few possibilities. One of the possibilities is that the poles are real. This happens when the factor inside the square root is greater than 0 or zeta is greater than 1. In this case, the two poles lie on the real axis and are on the left up plane, as shown in the pole zero plot on the left. The unit step response of the system is shown on the right. The response has two exponential components contributed by the two poles of the system. This system is known as the overdamped system. Now, a second case happens when the factor inside the square root is less than 0 or zeta is less than 1. In this case, the poles become complex quantities and are on the left up plane as shown in the pole zero plot. The real and the imaginary parts of the two poles can be readily found from the solution and are shown here. The unit step response of this system will not only have exponential component but will also have sinusoidal components. This is because the solution of the poles will have real part as compared to the overdamped system. This system is known as underdamped system. A special case occurs when zeta is equal to 1. In this case, both poles are real and are located at the same location on the real axis, as shown in the pole zero plot here. The unit step response in this case is similar to the overdamped case, but the response is a bit faster because zeta for this system is smaller than the overdamped case. This system is known as the critically damped system. A fourth case occurs when zeta is close to 0. If we use this limit on the pole solution, we can see that the real part vanishes and the poles omega p1 and omega p2 lie on the imaginary axis. We can then conclude that the time domain response will only contain sinusoidal component and no exponential component, as can be seen from the unit step response. There's another case which we'll not discuss here is when zeta is less than 0. In this case, both the poles lie on the right half plane of the pole zero plot, and the response of the system will have a growing exponential component, which would make the system unstable. Now, to further analyze the system, we need to also look at the frequency response and plot the Bode plot. In order to do that, we need to take the magnitude response and simplify it for different values of omega. For omega much smaller than omega n, the response is approximately equal to k, which is the DC gain. For omega much greater than omega n, the response is approximately equal to k times omega n square over omega square. And for omega equal to omega n, the response is equal to k over 2 times zeta. For zeta smaller than 0.5, in this case, we can see there will be frequency peaking. If we consider the first two cases and plot the frequency response, it will look something like this, as shown on the right. At DC, the value is equal to k, and at high frequencies, the frequency response drops at a rate of minus 40 dB per decade. This is because each of the poles contribute minus 20 dB per decade. In the middle, the response depends on zeta, and as shown here, for zeta greater than 1, the response will be of low pass nature. For zeta smaller than 0.5, there will be peaking, and for zeta equal to 0.5, the response will be flat, and it will give the maximum possible bandwidth. This is also one of the strategies exploited to extend the bandwidth of analog circuits. Peaking is often considered an undesirable effect, as it can result in overshoot. But there are applications where it is beneficial to have some amount of peaking. For example, in a wildland transceiver, as shown in the diagram on the right, the channel is often lossy which means that the channel has attenuation at high frequencies. So in this case, it is useful to have some peaking at the receiver so that the combined response can become flat and the bandwidth can be extended. This operation is known as equalization, and it's widely used. It's a widely used technique in high-speed data transfer across a lossy channel. Now let's take a look at a design example and see if we can extend its bandwidth. Here is a well-known single-stage common source amplifier with a load resistor R and a load capacitor C. By doing small signal analysis, we can find its transfer function as shown below. The DC gain is Gm times R, and the pole is located at 1 over Rc at the output. Now let's consider another circuit where an inductor is inserted in series with the resistor and everything else is kept the same. In this case, by doing small signal analysis, we can find the transfer function as shown here. Note that now the circuit has a 0 and 2 poles. By solving the quadratic equation, we can find the location of the poles as shown here. This result is compared with our earlier expression, and an expression for omega n and zeta can be found in terms of R, L, and C. Now by setting zeta equal to 0.5, the condition for maximum bandwidth without any overshoot is achieved. This condition gives an expression for L, which is equal to R squared times C. Now intuitively we can tell that that by inserting the inductor, we can have a faster response. This is because inductor opposes the change in current, and so all of the AC current initially flows through the load capacitor, charging it fast before the inductor current kicks in. We can do a quick SPICE simulation of the circuit to verify the analysis. For L equal to 0, that is without any inductor, the bandwidth is limited by the output pole of the circuit. For zeta equal to 0.5, which should have given a maximally flat response, we can see there is some peaking in the frequency response. This is because the transfer function has a 0. The peaking, however, can be controlled by zeta. By using a slightly larger value, a flat response can be obtained, as shown in the blue response. The system is still an underdamped system, but provides a substantial increase in bandwidth compared to the simple common source case. There are more advanced variations of the inductively peaked common source amplifier. The first one is called bridge shunt peaking, where a shunt capacitor is connected in parallel with the inductor. This helps to balance out some of the extra peaking introduced by the 0. The next one is called series peaking, where an inductor is connected in series with the amplifier stage and the next stage. The inductor L and the capacitor C2 is a part of the routing, and therefore any parasitics of the routing wires can be included in the design process. The next one is called T-coil peaking. T-coil is essentially to couple inductors with a capacitor at the center. It is the most widely used peaking technique and can offer up to 3 times the bandwidth extension. We'll talk more on T-coil in later videos. However, it is worth mentioning here that in any real design, a combination of these techniques is utilized to get a more balanced design. It is complicated to derive the transfer function for each of these variations, and therefore some sort of behavioral or transistor level simulation is necessary for optimization. So finally, these are a couple of good references if you want to dig deeper into the topic. So that's it for this video. Thank you for watching, and please subscribe to this channel so you get a notification whenever I upload a new video. Until then, take care and see you soon.